Hello. Today we're going to talk about polynomial functions, and we're going to look at three different things with polynomial functions. First of all, we're going to just look at kind of what they are, how they're written. Secondly, we're going to talk about evaluating polynomial functions. And lastly, we're going to talk about the graphs and some characteristics of the graphs of polynomial functions. But first of all, let's take a look at this. We're talking about what's standard form, the degree of a polynomial, and the leading coefficient of a polynomial. Well, as you can see, their standard form is when we write the terms in order from largest exponent down to smallest exponent. The degree is simply the largest exponent, and the leading coefficient is the number out in front of the term with the largest exponent. Okay? And I have a little example down here at the bottom. Okay? If I look at this little expression right here, this little polynomial, it's not written in standard form right now, but if we were to write it in standard form, we're going to look for the largest exponent, which is this guy, the third power, and we're going to go the second power, the first power, and then the constant. So in standard form, this one would look like negative 5x cubed plus 7x squared plus 3x plus 1. Okay, if I was to write it in the proper order. Secondly, if it's asking me for the degree of the polynomial, the degree is the largest exponent. I think we mentioned this in a previous lesson, but it's that one right there. This one would have a degree of 3. Okay? And then the leading coefficient is the number in front of the term with the largest exponent. And in this case, the number in front of that term is a negative 5. Its leading coefficient, which I abbreviate a lot of times, LC, is negative 5. And it's not negative 5x, not negative 5x cubed, it's just negative 5, the number out in front. Okay? There's something kind of unique about this. When things are written in standard form, the degree and the leading coefficient all come from that very first term out in front out there. Okay, so one thing you'll be doing is you'll be asked to write things in standard form and identify the degree and the leading coefficient. Hopefully not too terribly bad. Not a lot of fancy math involved in that. Okay? All right, the next thing we're going to take a look at is we can classify polynomials according to their degree. If something has a degree of 0, for example, and the degree has to be the power on an exponent, so it'd be something like this. 5x to the 0 power. Its degree is 0. Well, if you remember, anything to the 0 power is 1. So that's really 5 times 1, or just 5. It's just a plain old number. And there's a special name for just a plain old number. It's called a constant. Okay, so if something has a degree of 0, or basically if it doesn't even have a variable on it, it's called a constant. Okay, if something's largest power is 1, it's called a linear function. And these are the ones where we did like y equals 2x plus 7. Those were the y equals mx plus b problems, where the largest power was a 1. How about when the largest power was a 2? If I had something like this, it's maybe 2x squared plus 7x minus 3, where the largest exponent was 2. If you remember these were called the quadratic equations. Okay? So the largest power of 2 is a quadratic. 3, if it has a third power, it has a special name. It's called a cubic. Okay, that's something x to the third power, we can say it's x cubed. If I had an x to the fourth power, it's called a quartic. And then anything with a fifth power is called a quintic. Okay, and the way that I remember quintic is if a lady has 5 babies at the same time, they're called quintuplets. It's called a quintic. Quartic, there are 4 quarters in a dollar. Quartic, quarter, that's the way I remember that one. Okay, so we'll also be asked to classify a polynomial according to its degree. Okay. This page is in your book, something you can look at if you want to go back and take a look. But it kind of just summarizes the things we just talked about. Okay, it talks about standard form, the degree of a polynomial, and its leading coefficient. Okay, and there's some examples. Okay, if I was to look at this guy right here, for example. Okay, it's in standard form. It goes from the third power down to the smallest one. Its degree is 3, so it's called a cubic. Okay, and its leading coefficient is the number out in front, it'd be an 8. Okay. So again, not a lot of fancy math yet, just kind of identifying and defining some of the different parts of a polynomial equation. Okay. We talked about this also in a previous lesson about how to determine whether or not something is even a polynomial. Okay, and as it says there, we can't have negative exponents, we can't have variables in the denominator, we can't have radicals, no variables can be exponents. And this last one here where we can't have more than one kind of variable. What I mean by that is if I have like a 5x plus 2xy plus 7y. Okay? I can't have a term that has both an x and a y in it. Okay? The terms are all x's or the terms are all y's. Okay? It's either one or the other. So that's kind of what I mean by number 5 there. Okay? But again, this list kind of basically describes what polynomials cannot have. Okay? On the next screen here, they're going to have us go through and identify a couple things here. State the degree of the leading coefficient of each polynomial. If it is not a polynomial, explain why. So if I look at this first one right here, and I know they have the answers here, but let's try not to look at them at first. Is this thing a polynomial? Yes. Okay, it does not have any of those 4 things that I mentioned right here. No negative exponents, no variables in the denominator, etc. This one's all okay. Okay? If it is, tell its degree. Well, the first number out front there, the degree or the biggest power is a 5, and its leading coefficient is an 8, as we can read there. Okay? Letter B, this is not a polynomial because of this term right here. It has both an x and a y in it, which we can't have. Okay? And the third one is a polynomial. That's all good. Its degree is 4, and its leading coefficient is, oh, hold it, wrong one. I didn't look carefully enough. They did not write it in standard form. This is the biggest term. Its degree is 8, and its leading coefficient is -4. Okay, now most of the time they do write things in standard form, but every once in a while they'll change the order and switch it up, okay, just to try to trick us a little bit. So always look for the biggest exponent first. Okay, can we try these guys down here at the bottom once? Can we do the same thing? Is it a polynomial? 1a. Is that a polynomial? It is not a polynomial because of this term right here. We cannot have an x in the bottom. So we can't even, nope, we're done. Can't even do anything more. The middle one here, 1b, it is a polynomial. And if I look for its degree, its largest degree, I'm just going to write d equals, the largest power it looks like is a 6. And its leading coefficient, the number in front of it, is a 5. Okay. This guy over here, it also is a polynomial. It meets all 5 of those criteria. What's its degree and leading coefficient? If you look carefully, it looks like the largest power right here is a 6. So it's a 6th degree polynomial. And its leading coefficient, now I don't even see a number in front of the x there, but if there isn't one, we know that it's a -1. Okay? So we're going to be doing a little bit of that as well, identifying whether or not it's a polynomial or not, and then finding its degree and leading coefficient. So once again, not a lot of fancy math here yet. Okay, just kind of some vocabulary words. Okay, here comes a little math. This is the second thing we're doing today. We're going to evaluate a polynomial function. I think you guys have seen these before. Okay, here I have, the one on the left here is I have function f. F of x is equal to x cubed plus 2x squared minus 4. And I want you to evaluate f of 2. Well, if you remember, the way we evaluate functions is the number that's in parentheses here is the number that goes in for x in the f function. So what I oftentimes do is I rewrite that function, and wherever I see an x, I'm going to put a parenthesis. And what am I going to put in place of that x? I'm going to put in a -2. Okay? It's really, really important, I think, to write those in parentheses. And then I'm going to evaluate it. Notice the negative is also in the parentheses, so if you did this on your calculator, it'd have to be parenthesis -2 cubed, which would be -8. -2 squared is 4, +4, times 2 is another 8, and then -4. Okay? -8 plus +8, they cancel out, and we just get -4. Now you can certainly type all this in all at once on your calculator. Okay? I a lot of times like to do it piece by piece, bit by bit. Okay, but it's just simply substitution. Okay? I could do the same thing over here. I have function g this time. Notice this g is just naming the function out in front. G of 3, so I'm going to plug in a 3 everywhere I see an x. Okay, and if I rewrite that top one, it's going to be 2 times something cubed plus 6 times something squared minus 10 times something. And the number that's going in those parentheses is a 3. Okay, now if I evaluate this carefully, 3 to the third is 27. 27 times 2, that turns into 54 if I did it at my calculator. 3 squared is 9. 9 times 6 is another 54. And then I have minus 30. Okay? And you could certainly use your calculator, or if you maybe know in your head, I'm going to use my calculator a little bit. 54 plus 54 minus 30 I end up with 78 altogether for an answer for this one. Okay, so it's not too bad. It's just doing a little substitution. And notice the numbers that were in the parentheses here? They were numbers. We can plug or substitute numbers into an expression fairly easily. Okay, let's take a look at this. Ooh, same thing. But if you look carefully, what's in parentheses here now, it has a variable in it. Okay, we're going to do exactly the same thing. Okay, wherever I see an x in that top one, I'm going to replace it with 2a. Okay, and let's do the same thing. Now remember, this square right here only goes with what's in parentheses. And if I do 2a squared, I also have to square the 2. 2 squared is 4a squared. Okay, that goes to both of them. And then 4 times 2, I get 8a squared for that first term, plus 6a plus 1. Okay, and yep, a couple of them had a's in it, but they're not like terms because that does not have a squared. They have to have exactly the same exponents in order to combine them. Okay, and I get a simple, that's as far as I can go in terms of simplifying my answer. It's going to have a's in it. That's okay. We won't be able to get an exact number for an answer. Okay, this guy up here, same thing. Okay, I'm going to plug it in there. Okay, then I'm going to add on to it when I plug in a 5 to each one of those. Oh, now this is a two-part problem. So I'm going to do this one first, g of 3a squared. Okay, that's going to turn into 3 times something squared plus something plus 2. And I'm going to plug in a 3a squared for each of those. And then at the back end back here, I have plus 5, g of 5a. So I'm going to plug in a 5a everywhere up there at the top. And I'm going to put it down here. It's 3 times something squared plus something plus 2. And in the second part here, I'm going to plug in a 5a. Okay? And now if I evaluate all the little pieces here, again, I have to square each of those. 3 squared is 9. This is 9a to the 4th. Times 3, I get 27a to the 4th when I do 9 times 3. Okay, this is just 3a squared plus 2. If I square this part, 5 squared is 25a squared. Times 3 is 75a squared plus 5a plus 2. Okay, so I kind of get kind of a big long expression there. If I do my combined like terms, again, I like the biggest power first. Well, I don't see any other a to the 4th, so that's my first one. I don't see any a cubes, but I have a couple a squareds, these two guys. 75 plus 3 is 78a squared. Plus 5a, and then 2 plus 2 is 4. And I think that's what I end up with for a final answer on that one. So again, we can substitute numbers into these polynomials. These polynomial functions, we can substitute variables into the polynomial functions. Okay? And again, the bigger they are, the little bit fancier they are, the little bit more work they require. Okay? I'm not going to do this whole entire one here, but I want to mention this. Okay? Here's the function g of x. This is what it looks like in your homework. It's sometimes a little confusing. And I have two parts to this one over here. I have g of 5a minus 2 plus 3 times g of 2a. For the first part of this, I'm going to take a 5a minus 2 and plug it in to each part there. It's going to look something like this. It's something squared minus 5 times something plus 8. Okay, that's what this part would look like. And then it has plus 3 times g of 2a. That's where I'm going to take a 2a and plug it in there. So I'm going to have something squared, something squared something squared minus 5 times something plus 8. And what goes in these parentheses is a 2a. Out here went 5a minus 2 and 5a minus 2. Okay? So my point is this number here is just a multiplier. And notice how I put big brackets around it. Okay? Actually, the more I think about it, I'm going to work this up because you're going to see one, I think. If you remember, 5a minus 2 squared is 2 of them. So I'm going to write it twice and I'm going to FOIL. I'm going to do this kind of fast. I'm going to get 25a squared. Then I get a minus 5a, I'm sorry, 10a, and a minus another 10a. I get minus 20a plus 4. That's how that first one works out. If I distribute here, I get minus 25a plus 10 plus 8. Okay, now I'm going to go to this part. Oh man. I'm going to do this part in the middle here first. This is 4a squared minus 10a plus 8. When I just do the stuff in the parentheses, and then I have to multiply it all by 3. I'm going to get 12a squared minus 30a plus 24. Wow, we get a really, really big long expression there for that. Okay, I know I'm going kind of fast here, but take your time and work it out slow. Okay, here we go. Do we have any like terms? Do I have any squared terms? I think I have a couple right here and right there. And 25 plus 12, I think, is 37a squared. And they're done. Do I have any a's? Yep, I have a couple of them. I have negative 20, negative 25, and negative 30. If I add those together, I think these two are negative 45. Minus 30 is negative 75a. And again, you can use your calculator. And then they have some constants here. 14 plus 8 is 22. 22 plus 24 is 46. And I think that's what I end up with altogether on that one. Okay, so there are a couple tricky things about that one. Once again, there was this multiplier out in front. I just wrote it here and I multiplied everything in big brackets. And if you see a little expression like this where it's squared, you have to write it twice and FOIL it out. Hey, that's the trickiest one you're going to see. But again, the whole moral of the story is with these functions. Okay, we take whatever's in parentheses and we plug it in everywhere we see an x and write them in parentheses. Okay? So obviously, evaluating these polynomial functions, there's a little bit of math to it. Okay? The third and final thing we're going to talk about okay, are the graphs of these polynomials. And there's a couple little patterns here we're going to look for. Okay? If something has a degree of 0, if it's a constant function, it's just a straight line. Okay? A horizontal line, rather. A linear function, if you remember from Algebra 1, it's just a straight line. Quadratics were these parabolas. They could open up and down. Okay? And we haven't done a whole lot with the cubics, the quartics, and the quintics, but there's a possible graph of each one of those. What I want you to look for here, look what it says down here in red. Are there any patterns in regard to the degree of the polynomial and the number of zeros it has? The number of solutions, the number of zeros meaning the x-intercepts. Well, a degree of 0, it had 0 x-intercepts. A degree of 1, it had 1 x-intercept. A quadratic had 2. A cubic 3. A quartic 4. And a cubic or a quintic could have 5. Aha! There's a little relationship there, and it says it right up here in the last sentence. The degree is the same as the number of possible zeros that it has. Okay? If it had a 6th power, it could possibly have 6 zeros. In 8th power, it could have 8 zeros, and so on. Okay, we're going to take this a step further. Okay? We're going to break it apart a little bit. If it has an odd degree, okay, so if we had something like x to the 1st, x to the 3rd, x to the 5th, x to the 7th, and so on, it would have a odd, oh shoot, I'm doing the wrong ones. Okay? I'm going to start over here on the right. If it had a 1, a 3, a 5, a 7, and so on, if it had an odd degree, it's going to have an odd number of zeros. Okay, that's going to be the maximum number of zeros it has. Okay, so once again, if it's a third degree polynomial, it could have three zeros, or it could only have 1 zero. Okay, this is the maximum. If it was a 5th degree, it could have 5, 3, or 1. Okay, kind of see how that's working? If it was a 9th power, it could have 9, 7, 5, 3, or 1. But again, the degree is the maximum number of zeros. Okay, same thing with even powers. If I had x to the Well, x to the 0, x squared, x to the 4th, x to the 6th, x to the 8th, and so on and so forth. Okay? The degree here tells me the maximum. But if it's an even number, it's going to have an even number of zeros. Just like an odd degree has an odd number of zeros. And likewise, if I had an 8th power, it could have 8. It could have a maximum of 8, or smaller. It could have 6, 4, or 2, and even 0. Remember, 0 is an even number, isn't it? Okay? So an odd degree function will have an odd number of zeros. An even degree function is going to have an even number of zeros. Okay? All right. Lastly, we're going to tie this a little bit together here. Okay? When I talk about the end behavior of a polynomial, what you talk about is, let's suppose I had a graph of a polynomial that went something like this. When I'm talking about the end behavior, I'm talking about out here at the edges. Eventually, where does that graph go when I get to its ends, if you want to call it that? And these graphs are going to have two ends. Okay? The one over here that's way to the right. Okay? How do I describe those? I guess there's a little terminology that we're going to use here. When I go out here to the right, I'm talking about when my x values get bigger and bigger and bigger and bigger when I'm going to the right. And the way I kind of describe that is I say, as x goes to positive infinity. That means as I go to the right forever. Okay? So this means as x goes to positive infinity, I want to know what happens to f of x. And f of x is the y values. Okay, as I go to the right, where does this graph eventually go? It's going up, 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 up forever. And how do I describe going up forever? It's also going to positive infinity. Okay, so that's one direction. I described it going to the right. Well, I also have to describe going the other way. This guy out here. And when I describe that, I'm talking about as the x values go to the left forever. And the way I describe that, as x approaches negative infinity. We're going to the left forever. I want to know what happens to the y values out there. Well, in this case, as I go to the left forever, they're going down forever, and it would also be negative infinity. Okay? So ultimately what I'm looking for are these two parts right here. But we have to write this whole thing in terms of describing its behavior so I know which directions I'm talking about. Okay? If that makes any sense or not. Okay? Let me just mention it one more time. When describing end behavior, we have to describe both directions. Okay? Basically what this first one means, as I go to the right forever, what happens to the y values? And the bottom one here means as I go to the left forever, what happens to the y values? But just so we're all crystal clear, when you describe end behavior, you're going to have two parts to your answer. You're going to write this whole thing. Okay? This is going to stay the same for all of them. The only thing that's going to change is, do the y values go up or do the y values go down? Okay? So I'm hoping we're okay with this terminology, this notation that we're going to use in terms of describing what's happening out at the ends. Okay? Oops. Okay, and over here on the right, okay, I kind of have a little summary. I'm going to see if I can zoom in on that just a little bit here. Okay? And in the Google Classroom, there's an extra little attachment there by the assignment that says end behavior sheet. Okay, and I have a sheet for you that might not be a bad idea to print off. Okay, and it looks something like this. Okay, that has this stuff on the board on it, describing all the end behaviors. And there's some relationships here between the degree and the leading coefficient in terms of what the end behavior of a graph is going to look like. Okay, so first of all, if I have a polynomial expression, I'm going to look at its degree. If its degree is even, or if it's odd, and it's going to kind of cut it in half. If I had an even degree polynomial, I then look at its leading coefficient. And if its leading coefficient is positive, then as I go to the right, as x approaches positive infinity, it's going to go up. And as x goes to negative infinity, it also goes up. Okay, kind of what happens here, if it's an even degree, a leading coefficient positive, notice they both go in the same direction. They both go up, don't they? What if it's an even degree and the leading coefficient is negative? Well, as x goes to positive infinity, it goes down, and as x goes to negative infinity, it goes down. The end behavior is down on both of them. Okay? So, just to kind of summarize just the evens real quick. Evens, and there's a little note at the bottom of that little extra sheet there. If it's an even degree polynomial, they go the same direction, whether they both go up or they both go down. What determines which way they go is that if the leading coefficient is positive, they both go up. If the leading coefficient is negative, they both go down. Okay? What if the degree is odd? Okay, what if it's an x to the 5th power or an x to the 7th power? We look at its leading coefficient, and if it's positive, as I go to the right, as x goes to positive infinity, it goes up to positive infinity, and left goes down. If that leading coefficient is negative, as x goes to the right to positive infinity, it goes down, and as x goes to the left, it goes up. To kind of summarize an odd degree polynomials go in opposite directions. One goes up and one goes down. If the leading coefficient is positive, as you go to the right, it goes up. The left, it goes down. If the leading coefficient is negative, right is down, left is up. Okay, so it's kind of a nice little summary of all this end behavior business. Okay, you're going to see some questions like this, and these are the last ones for the day here. Let's see if I can zoom back to my screen. Here we go. Okay, all right, so what it wants us to do is it wants us to describe end behavior. So, as I describe end behavior, I have to write this. I have, very first thing, as x goes to positive infinity, what happens to f of x? And as x goes to negative infinity, what happens to f of x? And I always have this little bubble here. On the test in this chapter, or this unit, when you get to these problems, I will have this filled out for you. Hey, all you will have to do is you'll have to fill in the bubble at the end and tell me what's happening to the y values. But on your homework today, you're going to have to write the whole thing out. Okay, so I'm looking at this first one. Okay? As x goes to positive infinity, remember that means as I go to the right, where do the y values go? That's out here. They're going down, it would go to negative infinity. Okay? This one then is the other way. As I go to the left, as x approaches negative infinity, as I go this way, that graph also goes down to negative infinity. Okay? So that's what I'm doing here when I did the first part, describing end behavior. Okay? Determine whether it's odd or even. Okay? Well, they both went the same direction. Same direction is an even degree polynomial. So this one is even. And then it tells me to describe the number of zeros. Well, a zero is an x-intercept. How many x-intercepts are there? There's one right there, and there's one right there. It has 2 zeros. Okay? So it's more than likely going to be an x squared. I'm sorry, it could be x squared, it could be x to the 4th, it could be x to the 6th, it could be x to the 8th, any even power. Okay? So there's kind of 3 things there. Okay, what if I did this one on the right? I'm going to erase this here for a second so I can use my same writing here. Okay, let's describe its end behavior. As x goes to positive infinity, that means as I go to the right, looks like that one's going down again to negative infinity. And this one, as x goes to negative infinity, as I go up, as I go to the left, that one's going up to positive infinity. Okay, now those graphs, they go in opposite directions. Opposite directions are odd degree polynomials. So for part B here, this is an odd degree. We don't know what degree it is. Okay? But the second, or the last part, how many zeros? 1, 2, 3, 4, 5. It has 5, zeros, I guess they call them. 5 zeros. Okay? So that's the last thing you're going to be doing on your assignment today. I got 2 more down here at the bottom that I'd like to try. Okay? As x goes to positive infinity, what happens to f of x? And as x goes to negative infinity, what happens to f of x? And again, in describing the end behavior, that needs to be on your paper. Okay? You can't just write positive infinity or negative infinity. We need to describe, once again, as this means as I'm going right, and this means as I'm going left, and I want to see that notation. Okay? So in the one on the left here, as I go to the right, that guy's going down to negative infinity. As I go to the left, that guy's going up to positive infinity. They're going opposite directions. Opposite is an odd degree polynomial. And then how many zeros does it have? 1, 2, 3. That should be an odd number of zeros. It's going to be 3 zeros, 3 solutions. Okay? Let's do the same thing here for the very last one, 4b. Okay? Can I fill in the little bubble here? The first one, as I go to the right, looks like that goes to negative infinity. And this one, as I go to the left, it also goes to negative infinity. Okay? Because they go the same direction, it's going to be an even function, or an even degree, I should say. And how many zeros does it have? 1, 2. It has 2 zeros. Okay? So once again, if it were me, it might not be a bad idea to print off this little extra sheet that I have there by the assignment. Something to have handy to make reference to. And it looks like an awful lot of writing, but it's really not too bad once you get comfortable a little bit and practice it and use it a little bit. Okay. So there again, a quick recap of functions. We identified functions, different parts of functions. We evaluated functions. And lastly, we described the end behavior of functions. All right, thanks for tuning in.